went much farther, of course, considered various other abstract mathematical consequences. Here I would, however, emphasize that in the case of level lemma, there is one essential assumption, that's uniform probability. Independently, the same phenomenon was also discovered by people in the probability theory, and they, instead of functions of which are, say, smooth, they studied sums of large numbers of random variables, and they discovered that such sums don't deviate too much from the expected values. And again, there's essential assumption of independence. But even further progress was made by Azuma and McDiarmid, that they replaced sums by functions of random variables, but of course, not any functions, but again, functions that satisfies various kind of smoothness conditions. And again, most Knight's theorems hold for independent random variables. There are some results also for the case of dependent, which really for neural computing would be more interesting. We deal with real data, you often don't have independent variables, but then of course things become more complicated. So I will probably talk only on independent in this lecture, to at least explain how these things work. Now, I'm going back. Thanks for mentioning quasi-orthogonal dimension. This is basically how I became interested in this type of problems. And as I said, these polar gaps are small, so we can pack a lot of them on the sphere exponentially many. So basically, this is the idea. But it's really interesting that, in fact, one can, and this is what we really did with my colleague Paul Kanan 30 years ago or so, that we proved it using graph theory. Then again, such a quasi-orthogonal set can be seen as a clique in a graph, and using some powerful tools from graphs, one can also get to it. So you see, these things come from various directions. You can get it from, say, calculation of sizes of polar gaps. You can also get it from graphs. You can get it from sums of random variables. And again, you have the same phenomenon. Now, and then, of course, this is something that Alexander wrote a lot about. This is this curse and blessing of dimensionality, this very dramatic word, almost like from Shakespeare, that we mathematicians don't use very often, such strong words, but metaphorically, really, on one hand, these high dimensional things, of course, means that you have these unmanageably large numbers of parameters. On the other hand, you have this kind of basically concentration of measure, which means that sometimes random phenomena behave almost deterministically. There's another very nice consequence of kind of Levis lemma, is something that, but I won't talk about it today, but it has an impact on reduction of dimensionality, that projection to something log of the original dimension behaves nicely. And as I say, also this quasi-orthogonal dimension, you can store a lot of almost orthogonal vectors, which basically in many applications you don't care about little imprecision. But I would like to go back to neural nets. And in neural nets, we often deal with tasks that, for example, classification on large domains. But to imagine how many functions you have is this, and this is not from my head, of course, I read it somewhere, that if you take, suppose, a 9-dimensional Boolean cube 0, 1 to 9, so this is the set of cardinality 512, and consider all binary classifiers, then you get numbers that, according to physicists, are larger than all atoms in the universe. I don't know how they estimate these, but in any case, it's enormous. To something that really is huge. So obviously, we are not interested to build neural networks that would be capable of well approximating all these functions. It's too many of them, and most of them are absolutely uninteresting. And similarly, in the case of not classification but regression, again, as I said, there are these exponential increasing number of highly uncorrelated, basically nearly orthogonal functions again. So basically, we are not really interested in some kind of universality properties. We don't want networks that deal with all of them. Instead, we would like to focus on those that are relevant. So this is something that we focus on some relevance that one way how to formulate is to consider a probability. So you would like to approximate by neural networks some functions that are randomly chosen with respect, however, to some given probability distribution. Some tasks are highly improbable, almost maybe impossible, while others are highly probable. That's very likely that certain functions you would have to deal. And we would like to find networks that can compute efficiently functions that are highly probable. We don't care about those that are improbable, right? Here again, it would be nice to have results for all kinds of probabilities, but as the tools I mentioned, which deal with concentration, which means almost deterministic behavior of functions of random variables, and I would like to think about functions which are distances, approximation, errors, then it's easiest to consider that the random variables that are generated. So if you have a function, basically we have a function from some finite domain, let's say a large, to -1, 1, so binary classifier, then it induces these random variables, fx1, etc. And these are now random variables. And nice assumption that's good for, say, at least mathematical conclusions is that they are independent, which means that the probability is product. With my colleague Marcello Sanguinetti from Italy, we had some results also without this independence, but I'm not going to talk about them because they are kind of complicated. So I'd like to make things simple to express basic ideas. Now, this is the essence of my talk, really, of the results. And basically, intuitively, we combine two things. We consider a function of random variables acting on these randomly chosen variables by 1, etc., by m, as that's sufficiently smooth that we have to check whether it really satisfies some sufficiency conditions, because this concentration may hold, but if the constants are too large, then it's not interesting really. And another thing is that this, I will use the results that show that such of, in many cases, for many types of feed-forward network, in particular multi-layer perceptron networks, in other words, deep, the sets are relatively small. They grow only polynomially with this m, which is the size of the finite domain. And because they are small, and now, of course, the picture is kind of, it's very simplified, but you can imagine that you have these small, I mean, relatively small, not exponentially, but only polynomially growing set with m, and you have these small polar caps around, but we speak about I should be able to draw a high-dimensional Hamming cube, which I don't know how to do, of course. It's, so basically, there are these polar caps, which you can also look in discrete case. And those functions that are closed, there's not too many of them, I mean, relatively. And in addition, the set of all input-output functions is also small. So everything else, what's left, has the property that these are concentrated. But of course, one has to distinguish between uniform probability when there is the only, the mean value is always 0 for all functions H, which are input-output functions. But it's a different case when there is not a uniform probability, there is only product probability. Then they may be different, but we can look at the minimum of these menus and we get low bound. So this is basically intuitively explanation what I'm going to do now. Okay, let's go further. So I think Bob basically already said it. So this is basically what was in the picture. So first of all, we have to check smoothness of approximation errors. For this, there is McDiarmid inequality, which is called the method of bounded differences. And basically the idea is, and I like to call it coordinate-wise Lipschitz function. If you have a function of random variable, and if you change only one of its entries, then the whole function changes for a little, let's say some CI, but then the sum of squares of those CIs should not be too big, and then we have this kind of, I think I forgot to write the definition of gamma. But anyway, let's just only have the idea that it's something like coordinate-wise Lipschitz function, but with the coefficients that are small enough. And when they are small enough, then we get some, I think here I made a mistake, so sorry. One always makes a mistake. I think there should be P, and also I didn't define gamma. Well, nothing is perfect. Usually when I present lecture, there's always some little mistake on my slides, even if I check them. Well, so anyway, but the idea is that we have to check, and indeed one can prove that for L2 error on functions that are binary valued, these conditions needed for application of McDiarmid inequality are satisfied, and so one can prove that basically the function is smooth enough, so we can apply this type of concentration. Now we'd like to combine this with estimates of sizes of sets of input-output functions. And here we go back to history, because this is Schläfli, who lived already in 19th century, and he was interested in finite dimensional geometry, and he estimated size of the set of, say, suppose you have m points in d-dimensional space. You can, the number of subsets is of course 2 to m, but how many of these subsets can be created by cutting the set of m points into 2 halves by a hyperplane? And not too many, much less. So basically, the subset of m point set in R2D is called, that is created by a dichotomy, so linearly separable dichotomy. You cut by hyperplane, and you look how many of subsets of m point set in d-dimensional space can be obtained this way. Hyperplane in neurocomputing is something that corresponds to perceptron. So this is a function that simply assigns to one half state plus one, the other one minus one, and there is this hyperplane. And it's not too many really. As you see, here is the formula, already going back to slightly. This PD is the set of signum perceptrons, if you like, or set of all characteristic functions of half spaces, those that are separated by hyperplane. And we see that it grows with m, the number of points, only polynomially, where d is the degree. So points are in d-dimensional space, there's m of them, and well, all subsets of m points is 2 to m, so it's much, much more. And this is, for example, for the concrete case, when the set of m points is simply 0, 1 to d Boolean cube, so you have 2 to d points, and we know, of course, that all subsets is 2 to d, while those that are obtained by cutting by hyperplane are only 2 to d square. So as you see, polynomial versus exponential. So this is classical. It's a nice paper by Kůrková from 60s, I think, because it's difficult to read papers written in 19th century. And next step is the concept of growth function, which was introduced by Vapnik and Chervan and Case in connection with concept of VC dimension. So basically, we can look at this also as a growth function. If we fix the family of, say, hyperplanes or characteristic functions of hyperplanes, and look at this as a function of m, we see that the growth function is 2 to m to be divided by d factorial. But more generally, if you have a family of functions which say values -1 plus 1 on some set u, then this growth function is that you consider all m-point subsets of u and look at the cardinality of the set of functions that this family A say generates on these m-point sets. So you see, this is basically very similar. Before you had m-points, and the family was characteristic functions of half spaces. Now you have a general family binary valued functions, and you look at all m-point sets, and when it is largest, the largest would be probably if they are in some kind of regular position. And that is called growth function. And that's, as I say, kind of old concept, maybe older than most of you here. This, it's quite interesting how things that originated by people who studied completely different problems become quite handy when you study neural nets. So that is really nice. So, and this is really, growth function is related to VC dimension. Here is this Shellac-Sauer theorem that says that this growth function is bounded by, this is again, you see that is a polynomial where the exponent is VC dimension. So there is a polynomial. So again, when there is finite VC dimension, you still have a polynomial growth of the growth function. So, and becomes very handy now here when we would like to estimate sizes of sets of input-output functions computed by networks with, say, output unit which is ±1, so a linear output which is combined with a threshold. So that's kind of very handy and has been already studied by people, but they studied it, of course, because they wanted to do something with VC dimension. So here is a result that is quite new, and it's due to Bartlett and his colleagues, and it's upper bound on growth function of what? Of something we are now very interested, and this is set of deep perceptron networks. So what kind of, so let's look first to to which type of input-output functions or which type of network this applies. So we have, at least we Bartlett considered functions that are input-output function of a network that has single threshold, plus minus one output. So basically we can call it signum perceptron if you like. Then it has L layers. And in every layer, there is a perceptron with not now signum, but piecewise polynomial activation function. So it computes some activation function psi composed with an affine function. And they considered that these are piecewise polynomials with plus one pieces and degrees at most delta. So for example, these very popular ReLU functions are piecewise polynomials. They have two pieces. There is 0 and then there is a linear. And the degree is at most 1 because it's piecewise linear. People also consider RePU units, which are basically piecewise, like quadratic, for example. Also basically there's bigger degree. And of course, this RAM sigmoid would be 3 pieces because it's 0, then it's kind of x, and then it's again 1. So it would be 3 pieces and degree at most 1. Or say classical heaviside perceptron, that would be 2 pieces and degree is 0 because it's constant. So it's quite so. But what is of course interesting for us nowadays is that there is this number of layers, in fact. And so let's look at the upper bound. So basically, what I would like to take this upper bound on the number of input-output functions, which in many cases is still relatively small, those on the polynomial, and combine with these exponentially small neighborhoods, and see that there is still a lot that remains, and there are these concentration measured phenomenon. So let's look at the Bartlett's bound. I must say honestly that I simplified because they also consider something not only depth but also effective depth, which takes into account not only the number of layers but also the arrangement. But that would even, I don't like to complicate the technical formulas, even this is kind of not very comprehensible. But if you look at it, here we have M, but M is what we are most interested in. This is the size of the domain, the number of random variables. M, which is here again, it is a polynomial, but let's look what is in the exponent. L is the number of layers, and W is the total number of parameters in the network. And here are some constants that would be fixed when we fix the number of pieces and degree, and also the number of layers. So this is the situation, for example, of the mostly interested case today, and this is the ReLU. Then we fix delta 1, P is, I think, also 1 because we consider P plus 1 pieces. So basically, and we can study what happens as we increase the number of layers. Let's see. So now let's put all these things together. So we obtain a probabilistic lower bound on in this case, I consider L2 approximation errors of classifiers of the set of large size M by what? Deep ReLU perceptron network with signum perceptron output L layers total number of parameters W. This is just a special case. And now let's look what happens if the probability is not uniform. Then for each input-output function H, we have minimum. We have a different mean value of L2 approximation errors. So but for uniform, it's the same, which is in fact square root of M, which They are nearly orthogonal, so the distance is orthogonal. But in general case, it can be pretty different. So if we are interested in lower bound, then we take minimum, and we obtain this kind of lower bound that's probabilistic, that with probability, and now we have 1 and minus, and here is the upper bound on the size of the set of input functions multiplied by this exponentially decreasing size of polar caps, let's call it this way. And if this basically, this is small and this may not be so small, so we will have a large probability that for any randomly chosen function, the L2 distance is greater or equal of this minimum of the mean values. And minus some lambda, which is small, let's say, small enough, simply not to outweigh this exponential increase with m. You can take it as, I don't know, 4 root of m, for example. And what happens is that we see that if this mu h is large, then basically it means that almost all functions are very poorly approximated. So you get a kind of negative result, large low bound. On the other hand, if there exists a function for which this mean value is quite small, then I haven't written the other part of the concentration inequality, then there will be almost always in this small neighborhood. So this gives some, at least theoretical, it's a question how to practically really check it, but it gives you some at least global insight on this behavior. There is really this phenomenon, and what's interesting is that those sets of input-output functions really don't grow that fast. Yeah, so basically, maybe I should still say here, of course, you still, if you don't want to have this concentration phenomenon, you would have to choose network where the number of layers or the total number of weights also somehow would outweigh this factor. But this would mean, but we don't really want networks with, say, a number of parameters that basically grow with the size of the domain M. This is huge. You would like to classify really huge numbers of data, and you wouldn't like, if you would like to have network with as many parameters as the size of the set to be classified, it would be basically useless. Yeah. No, it's randomly chosen. I don't know. This is the problem really, because F is randomly chosen with respect to what? There's some probability, and the question is, and big question, how to characterize these probabilities? Obviously, and that was, as your colleague just talked, there are cases when certain phenomena are highly improbable and others are, highly probable, etc. But that's a question how to characterize such probability distributions modeling relevance. So this is a probabilistic. It means for the probability that the distance of f from the set of input functions, L2 distance, is greater or equal this, and the probability is that if the function is uniform, we would have something related to universality, which I'm going to talk about, basically about that universality really is something that doesn't have any practical application. But if it's highly improbable, if highly non-uniform, various things can happen. But the problem is how to characterize that probabilities. Now I'm going to this uniform distribution, which gives us at least some global point of view. So if you have no prior knowledge, then there is implicit assumption of uniform distribution. But in this case, we see that basically, when we have uniform distribution, the mean value, which the minimum of mean values of those, so a minimum over the whole set of all input-output functions of mean value of L2 distances from this particular function, because they all have the same mean value because it's uniform. There is this kind of symmetry. In this case, square root of m is the L2 distance. In other words, they are nearly orthogonal to every h. And so basically, we have the same minimum. So that's a very simple case in this case, because we don't need to deal with any minimum. They are all the same, but it's large. And so it means that when basically we would like to consider some kind of uniform distribution and some universality, it shows that if we don't know anything and we study this universality, we see that unless the set of input-output functions is large enough to outweigh this e2 minus m lambda for some small lambda, then basically most functions, and this is again this kind of simple picture, basically if the set is small, but small meaning polynomial with m, then still almost all functions which are not in this small, say, polar caps have large distance. So this is what happens is that basically this all kind of universality results are practically useless. This is something which is, I could call it paradox, because theoretically, if the set of input functions has some kind of finite DC dimension, and as we know in many cases it is the case, or doesn't have too many parameters, it's still small. Most functions really are highly uncorrelated with these input-output functions because of this concentration. They are not in these little polar caps. So you would say that, wow, now there's so many of them, a huge number, so maybe we can easily find some, but this is the paradox. It's not so easy to construct them. And it's something that it's very difficult for us to think about such kind of functions. And the reason is, and I think it's related to central paradox of coding. I really like the title of this paper. Any code of which we cannot think is good. This is the paper from coding theory. And of course, what is a good code? Good code is difficult code. It is a code that's difficult to break. And there is some theorem called Gilbert-Warshamov bound that says what is the maximum size among codes that's given spread and length. Spread is like distance in Henning distance. And although, again, it is known that if we pick a code at random, that it's almost likely that it has this, it is a good code, but it is self-construction is an open problem, and there have been very smart people working in coding theory. So I don't know the up-to-date information. Maybe someone discovered, but so you see that. So it's kind of something quite interesting that we know that if we consider this uniform probability, which is related to some questions of universal approximation property, there should be huge number of functions that are highly uncorrelated, have large distances from many sets of input-output functions, those that don't grow exponentially with the size of domain, as we have seen by this result by Bartlett. It is in particular applies to deep perceptron networks, unless they have layers, too many layers or too many parameters, but it's still difficult. So on the other hand, there's some old result by Ito from 92, and I call it not universal approximation, but even universal representation property. And it says basically that if you have a function on a finite domain, that's why the right representation, such a function can be exactly represented as a input-output function of a network that's linear output, and times of computational units. And basically the proof is very simple, and it is about linear algebra. What Ito did is that he basically proved that for some classes of neural networks, you simply has you basically can find these coefficients by solving a family of linear equations, meaning that you can find units that form some non-singular matrix. And it's really known, and it's even people studied it in coding theory, signal processing, that for many, and people use it, dictionaries, the word dictionary of computational units, or atoms sometimes call it in signal processing. So in many cases, if you have sufficiently rich family, and this is the case of many dictionaries in neural nets, then there exists such a representation, exact, that's why it's called universal representation property, and not only that, there's plenty of them. So that's why such dictionaries are called overcomplete. That means that there are many. In contrast, if you have something orthogonal, you have only unique. But in the case of these, there's quite too many of possibilities. Okay, it's nice, right? But of course, notice this M. Yes, but these proofs prove that you can have a linear representation with as many terms in the linear combination. So you can look at it as a neural net with linear output that has as many units as is the size of the domain. So as again, it's too big, of course, for large classification problems. So what about maybe it's possible to do it with less, maybe because these universal results usually assume something too big, unnecessarily big for many cases. But the problem is that the minimization of this number of non-zero coefficients in such a linear combination is a difficult non-convex optimization problem, because so-called L0 pseudo-norm, which is not a norm, is the number of non-zero elements in a vector, is simply not a norm. Really, it doesn't have nice convex unit ball, and the best approximation in the sense of something that already convex is L1 norm, because then it's convex, and because this is even not this. Of course, I cannot draw this L0, it's unbounded even, so these are the approximations. So L1 norm is very popular in lasso, in regularization. The nice thing is that it penalizes very small output weights and as well as few large ones. But why I am now interested is that it is really related to my favorite concept of variation in norm. So let's consider a function f and consider all exact representation in terms of linear combinations of functions from some set, bounded set G. And if the set G is kind of overcomplete and there exist a lot of them, we can look at all L1 norms of such representations, and we can of course minimize. But what happens is that if you simply formally take this minimum of these L1 norms, one can prove that it is a norm and has even a nice geometric interpretation. Basically, you can look at it as a norm that is obtained as Minkowski functional, which means that it is basically the norm that has unit ball, which is convex ball, or if you like, you can close it, of basically G with minus G, because every norm is generated by its unit wall that has to be symmetric and convex, right? So you have to take G and create the smallest norm, and it means that if you have a function f, you look how much you have to enlarge this unit walls so that the function fits in, and this is its norm. Or you can, on the other hand, you can also look how much you have to shrink the function so that it fits into the unit wall. This is just Minkowski functional of a convex body, and this. Using Hahn-Banach theorem, one can also prove that this G variation is related to inner product, which the function of which we like to calculate this norm with functions from the set G. And in other words, if it is nearly orthogonal, it has this variational norm. And this brings me to concrete construction. So although I said that they are difficult, there is one that one can still obtain for signum perceptrons, which are small, as we know from Schleifer's result. And this construction can be obtained for functions on square domain, and such functions can be expressed as matrices. So this is a Hadamard matrix. There are two matrices in fact, there are Sylvester-Hadamard matrices of different orders. And Hadamard matrix is a square matrix with -1, +1 entry, such that two columns or two rows are orthogonal. And so we can also consider that, let's say, for example, this is the square domain X. And there is a function defined by this ±1 as it is black and white. And one can prove that the inner product of these functions with functions that are induced by, say, cutting this square domain into two pieces by hyperplane and assigning -1, +1 are small. Which means that basically this is the nice property of Hadamard matrices, that this -1 +1s are not exactly but nearly evenly distributed. So if you consider -1 +1 on, say, one half on the other, then there will be some kind of cancellations, because you will have inner product would be small. So this is nearly orthogonal to all perceptrons, and this way one can go below bound. These are again, ancient concepts. Sylvester-Hadamard matrices going back to the 19th century, and this type of, they are really in the picture. These are generated by basically start with this small matrix, and then you just replace this one with the copy, and -1 with copy with sign minus, and this way you obtain this. And again, this is a very important concept, because basically rows of such Sylvester-Hadamard matrices form Fourier basis of such a Boolean function. So these are, as you see, these are all these concepts that have many other uses in mathematics. And in fact, this is interesting that although if you have this variation of these functions generated by these Sylvester-Hadamard matrices, which are nearly orthogonal to any perceptron, so meaning that they have large variations. So on the other hand, if you would like to compute such functions with two hidden layers, you can easily do it, because these are compositional functions. They can be written as -1 to u times v, where you denote these rows. And so it's just a brief, I don't want to go to any details, that if one looks for these kind of highly improbable or difficult to find, one can find using some kind of matrices. And in certain Hadamard matrices are extremal. They have, I think, the largest determinant among all matrices 10 times n. And that's the last thing I would like to mention, which because I'm very fond of this. It is something I got from a book by some guy called Manfred Schroeder, like Geneva Chancellor, but Schroeder. He's a guy who worked in acoustics. And in acoustics, they use something, pseudo-noise sequences and matrices, which have a lot of properties mimicking properties of random sequences, but are not random. They are generated. Although it's kind of very long segments, and anyway, one can use them to construct these Hadamard matrices, the cyclic matrices. And what's interesting, and that I would like to mention here, is that those pseudo-noise matrices, pseudo-noise sequences that lead to Hadamard matrices, which I try to persuade you that are difficult to compute by perceptrons, are nearly orthogonal to all of them, and they are really used. And so these are something which is not exactly random, but pseudo-random, but can be constructed in contrast to something random. And the real applications, and that book was about real applications in acoustics. For example, if you are in a concert hall, you'd like to test acoustics, and you cannot do it in empty hall because it has got totally different acoustic properties. So you need to have a hall full of people, but then you don't want to produce some nasty sounds. And these are basically inaudible. It was also used to make something invisible for radars. So it's something quite interesting that these kind of things that are specially designed to be invisible, inaudible, nearly random. These are those who are also highly uncorrelated with perceptron. So it's just to show you only something almost philosophical that. And this is what I really believe, that that basically I'm skeptical to this type of universality result because I try to persuade you the sets of input-output functions used to neural nets are relatively small or growing a polynomial with size of domains or sets of data to be classified. Yet, for most tasks, it somehow works. How possible? Because we know that most functions are not very correlated, have large distances. And the answer is that they have not chosen. The tasks of interest are certainly not uniformly chosen. We don't really need some universality results. Instead, we encounter something that's say created by nature or defined by human mind that is certainly not random. That's something which is maybe only concentrated. Maybe I shouldn't use this word because it was used in this lecture in different contexts. But they are the probability describing relevance is something really far from uniformity. So let's see. This is the point of view of mathematician from point of view of high dimensional geometry, and certainly I cannot conclude about some practical consequences, but tells us something only that basically if we assume that there is, and I believe it is what we should assume, there is some non-uniform probability, then in many cases, two possible situations occur. Either, and that's bad luck, that the minimum of these mean values is large, and then that model is useless because it will not really provide for the task of interest good approximation because of this concentration phenomenon that most functions of interest, say most problems we encounter, will have large distance if this is the minimum of these mean values, because it will be approximation would be bigger. Or with luck, there can be properly chosen, and it may be that the mean value will be small. But of course, the question how to find it, right? Nobody knows. I don't know. So maybe it may be a bit dissatisfying for people who are more practically oriented, but at least it's some global view from the point of view of high-dimensional geometry. That's all. Thank you.
Any questions from the audience? I got a question. I was thinking about this more around how the show.
Yeah.
And one of the things in mind was about using multiplicative seconds by approximation problem with scales. And then because that was done, so in some sense it becomes potential physical success of the scheme, right?
So you mean that the domain has different scales, or?
Well, actually, the name is the same, but it's just this set of functions that I'm using it as a stack. That's a change.
That's it. The big kind of whatever input-output function. So you change the number of layers, for example, or units, or something.
For example.
But you change it by what rule, or what? You change it because you get some output, you don't like it, so you.
For example, I start from a small picture.
And you add.
And then, so I think the way that result can be used to check for the feasibility of that scheme, because you have this number parameter, so it depends on the probability of me picking an answer from the way an answer, number away from the minimal. If that probability is very small, then it means that I'm actually doing this. Maybe that would be used.
Yeah, but the problem is that if we don't know the probability distribution of the task, we would like how we can estimate the mean value. Yeah, but as I say, the assumption of course, it is the easiest when we have a uniform probability, because then, of course, we know what is the mean value by simply. But on the other hand, I don't think it's because, as you see, there's just so many of these functions. So it's not, it doesn't have sense to consider that every problem, every task is chosen randomly, uniformly, because millions of them are absolutely uninteresting.
Just because there is this picture of approximating that by
Yeah, I'm very interested in this, but you know what is a problem? Suppose that I would like to apply this concentration phenomenon on basically predicting almost deterministic outcome of using some random choice of parameters. But what happens is, so supposedly we choose a random parameters uniformly. And we have a network where the function is nice in the sense of Lipschitz, you have the parameter. But the problem is that something happens with the uniform probability as it goes through the network. You see, this is the problem, and it changes because so the uniform then you don't get uniform probability of input-output functions. So that's the problem really. That I don't know how to, but definitely it's very interesting because many people today use random network. Either they say replace some part of parameters with 0, which means isolating them, or they choose some. That's very interesting topic, and it would be certainly very nice to get some conclusions from all kind of these concentration theorems, many of them, but not so simple. That's the problem, that these are these theoretical questions. We have beautiful tools that we inherited from previous generations of great mathematicians, but it still does not give us the answers people like to hear from us.
Thank you very much.
Thank
Yes.
you.
We got so much to discuss.
Oh, yeah.
No, but after certain years of purpose, purpose, say certain years of purpose, so I understand that there are no, there are no good or bad algorithms. There are good or bad understanding of reality. And in that sense, your last thesis, some real tasks. I guess that our understanding of what does it mean real task is the most important question. Could you bring some lines, just list? What do you think what's the real task? Because definitely not a random.
No, real task is, for example, what this PhD student is. She's studying the real task. She has some data from quantum physics, for example. Many people deal with.
But what's that? So,
many people here probably deal with real data.
yes, but you see, because many probabilistic many probabilistic estimates are created for random things, for random vectors. Right?
That's true.
Yes, and it's definitely not useless, but in high dimension more or less. Therefore, in high dimension, we need to view, see what can be good understanding in model of the real tasks. Or just work with some real tasks. It's classical. Just forget about universality and work with some classes of real tasks. And then, but if we work, then I should understand. We work with some benchmarks. We can lose the feeling of reality at all, because as a classical example, some software devices that recognize faces in lab online perfectly fail with the real police practice. And this is a good example. Therefore, in operational conditions, many are in fact because operational conditions are in. Therefore, I would like to have you extract here. Not the same.
I'm not like that.
No. You definitely want to talk with person. What is your guess? What to do? Maybe just teacher take different. No. Because it's.
No, but I think what Ivan said that he's basically, and this is what people are very good in practice. They just, if something doesn't work, they try to add something or enlarge.
Right.
I think it's the philosophical.
Yeah.
No, it's extremely practical question.
And practical at the same time.
Yes, it's extremely practical question because there are so many failures and so many catastrophic developments of AI.
Yeah.
So this, when we view also given skin that some good theoretical stability can be useless because they are not practical. Therefore, give a question, what has been practical?
That's a question, but I tell you what I would at least have a message is that some random task behaves almost deterministically. And that's a kind of good news, let's say, that probably this random algorithm, but it's not so easy to do it in a provable way. Let's say, well, yes, if you just make this planning, you take away some parts of net too big and delete with zero, etc. And it's in some cases it really does work, and it will be good to be able to prove why it does work, but it's not so simple to do it normally. But on the other hand, there are also kind of some of the negative messages of this lecture that we kind of these universality results are really not very interesting, let's say, from practical, but they hold, but there is a price for universality, which means that it costs too much.
Thank you very much. Yeah, so I'm in question. I'm somehow very for a while. This one time to close lecture.
Thank you. Yeah, thank you. Yes, it was an honor to lecture in this famous place.
Thank you.